Hello, everyone. Welcome back to this second session for the Emergency Nations and Risk Management track of cyber science. Our next speaker is Lukas Gressl. I hope I pronounced your surname correctly, at least. He's presenting us a paper titled Towards Security Attack and Risk Assessment During Early System Design. So, Lukas, are you with us?
Yes, hello.
Hi. As per the previous speaker, you have approximately 20 minutes for presentation so that we leave enough questions. So if you feel like you're running a bit late, I'll probably just drop you a quick private message in the chat. For the attendees, please make sure that you ask your questions through the Q&A feature that you see at the bottom of the screen. Lukas, over to you.
Okay. Hi. My name is Lukas Gressl, and today I want to present to you our work on security attack and risk assessment during early system design. I'm a PhD student at the Technical University in Graz, Austria, and I'm working at the Institute of Technical Informatics. Our industry project partner was NXP Semiconductors Austria, and our research was funded by the Austrian Research Promotion Agency. The focus of my research is the design of secure embedded real-time localization systems. So why is it necessary to consider security already at the beginning or the very first phase of system design? Simply because, first of all, it is really hard to integrate security into already existing systems. And second, because in the last decade, the number of reported security incidents has largely increased, also due to the fact that more and more IoT devices are deployed everywhere around us and integrated into our daily lives. So, for example, IoT systems are also used for entry systems, and these can usually be hacked using basic replay attacks. Also, car manufacturers are vulnerable to such security incidents. The most prominent incident in the last couple of years was the Tesla Model S hack, which was performed by a team of the KU Leuven, who were able to find out that the Tesla Model S key fob and car only use a very weak 40-bit encryption key, and due to reverse engineering, they were able to compute rainbow tables and thus quickly find out what key materials is used on the car and on the key fob. So to mitigate these security incidents, we have to consider security threat analysis. So for example, one of the most prominent ones is the STRIDE threat analysis, and also the CIA triad for assessing security requirements. Furthermore, there is also a big research area which focuses on security risk assessment and management, and which is widely used in network security assessment using Bayesian attack graphs, but also using risk trees on company level or whole system levels. In the first phase of system design, design space exploration approaches are widely used. This is a research area which has a lot of publications in it, considering classic design space exploration frameworks, which consider power and performance of embedded systems. In recent years, also security constraints are additionally considered in these design space exploration frameworks. but they are either very abstract or they only focus on very detailed problems. Hence, we saw a gap that there is no holistic view for security and classic non-functional requirements. And we try to close this gap by introducing our framework, which allows the integration of security constraints described as security requirements and assets, Bayesian attack graphs and risk trees, and security capabilities. Furthermore, it adds the security performance overhead and power consumption to the performance and power model of the embedded systems, and hence enables the consideration of the trade-off between performance and power consumption versus security constraints. Our framework is based on the well-known DECIDE framework, which uses a constraint programming approach to describe the mathematical problem of design space exploration. It is available on GitHub. And based on this framework, we implemented our framework, which is a security enhanced design space exploration tool. It consists of certain input views, which enables the designers to model the system behavior, the security attacks as Bayesian attack graphs or risk trees, which are based on risky model, and the description of the system architecture. Based on these inputs, the framework delivers an output of solutions describing the design of embedded systems. And this consists of the system partitioning, the task allocation, furthermore, the calculation of the security vulnerability and its security risk, and also the system performance and power consumption is calculated for each solution. So the functional perspective lets the designers describe the behavior of the system using a task graph. And in this task graph, each task performs a set of operations on a set of data entities which come with certain security requirements, which are taken from a pre-performed CIA analysis. With this representation, we solve ambiguous task and security descriptions. The architectural view lets the designers describe the potential architecture of the embedded systems using processing elements which come with distinct modes, which come with different power consumption characteristic, security mechanisms, and implementation vulnerability risk. These processing elements are connected via communication buses. The attacks are described using Bayesian attack graphs and risk trees. The Bayesian attack graphs and the risk trees both model attack steps as nodes in these graphs, which represent attack steps aiming at certain tasks in the task graph. Each node has an attack type, which matches the security requirements of the data elements operated by the tasks. Furthermore, each attack step is described in the BAG as with the attack success probability given as a conditional probability table, and in the risk tree with vulnerabilities, frequencies, and certain impacts. And in the end, in the BAG-based attack description, we are interested in the unconditional probability, success probability of the attacker reaching the attack goal, and using the risk tree on the mean risk value induced by the attacker successfully reaching the attack goal. So using these inputs, we try to find an optimal task partitioning and a task mapping and system partitioning. And for the task mapping, each task implementation is on a PE running in a certain mode is described with worst case execution time of this implementation. And the framework makes sure that all the connected tasks in the task graph are also reachable when they are mapped to the processing elements. The security mapping consists of two steps. The first step makes sure that each task mapping or that each task operating on a set of data entities mapped to a processing element is capable to secure the data entity security requirements. This mapping is basically described by certain rule sets which are extendable by the designers. The second step is that for each attack, the framework calculates how the attack steps can be mitigated by the security mechanisms offered by the processing elements the distinct tasks are mapped to. This is done by applying the implementation vulnerability to the conditional probability table and the vulnerability of the attacks aiming at the tasks mapped to the distinct processing elements. The attack success probability of the attack steps is estimated by the common vulnerability scoring system. And as the probabilities of the distinct attack steps propagate through the Bayesian attack graphs and the risk trees, adding these mitigations to the attack steps changes the unconditional attack success probability of the distinct goals and also the mean risk value of the goals. In the end, a solution is only considered to be secure if all the thresholds of the Bayesian attack graph or the risk tree hold. Furthermore, the framework offers a combined approach which allows the computation of both risk values and attack success probabilities. So here we have a short example of a attack scenario with a system functionality, the mapping of the tasks to the system architecture. And as we can see here, the security attacks are not efficiently mitigated because both the mean risk value and the unconditional probability of the attack goal A3 exceeds the threshold of A3. But using the right mapping, this success probability and risk value can be reduced, and therefore such a solution would be considered to be secure. We performed the evaluation using a use case, which is based on a secure indoor localization system. It consists of different nodes and anchors, and the nodes must get localized by static anchors. The architecture of the node and the anchor are comprised of an ultra-wideband radio, an application processor, and a secure element. And on these components, we described potential attack scenarios, which we evaluated with our project partners. Furthermore, the use case is described as a ranging process using a task graph. And we evaluated the usage of the BHE-based and the risky-based and the combined approach to model the attack scenarios. Also, the worst-case execution times of the task mappings and the security performance power overhead was provided by the project partners. The outcome and the solution space given by the framework can be seen in these scatter plots, or green dots in the scatter plots are considered to be secure solutions. Furthermore, we ordered the solutions based on their normalized performance and power consumption. Here we can see that the BHE-based solutions, or the BHE-based approach, gives us the most secure number of secure solutions. However, the risky based approach, because of its introduction of risk values, reduces this space vastly. The combined approach also gives the same number of secure solutions compared to the risky based approach. So basically, the reason why we introduced this risky-based approach was that we saw that the why we introduced the combined approach was that we saw that the risky-based approach needs a lot of computation time compared to the BHE approach. This is due to the underlying computation model, which uses probability distributions in the risk trees. And when we consider the fastest secure solution found by the BHE approach and the risky approach, we see that the BHE approach provides as a fastest secure solution a solution which uses a secure element which is less secure rated than the risky based solutions. This is considered due to the additional risk consideration provided by the risky approach. So our framework allows the integration of security constraints both from the perspective of attacker, both based on BHE description and risk tree description, and it allows the designers to outweigh the security risks and the over performance and power consumption of the system. The limitations are that the security attack scenarios are largely based on expert knowledge, and that there is no general method for judging the security mitigation of attacks by hardware components. Here we also relied on expert knowledge within our project partners, which was largely based on common criteria certifications and the usage of the common vulnerability scoring system. So thank you for your attention, and I will happily answer your questions. Thanks.
Thanks, Lucas. It was a very interesting presentation there. And I think, so we still don't have any questions yet, but they might be coming in the next few seconds. They must just still think about that. In the meantime, let me just remind everyone that after this talk, we will take a 30 minutes break. And so we'll be back at 2:30 p.m. UK time, so GMT +1, with another parallel session. And then that will be followed by the keynote speech at 4 p.m. So just make sure that you keep track of all different sessions going on. There are lots of moving parts in this conference. I hope you are enjoying that so far. If anyone has any question for Lukas, I think now should be a good time to put them in the Q&A. I would also like to remind everyone that we're interested in your opinion and your experience on cyber science. So there is a link for an attendee survey on the attendees attendee area on the website. So please make sure that it would be great if you can spend just a few minutes to tell us to let us know what you think, what your experience has been so far, and if you have any recommendation on how we can make things better. So Lukas, I don't see any question coming through, so I think we can wrap this session up a bit earlier than we thought. Thanks again for your presentation, and hope you enjoyed the conference so far. And I hope to see you in the next talks for the rest of the day and tomorrow. Thank you all, and see you at 2:30 for the next parallel session.
Thanks.